Okay, so let's start with the first question, which says, which of the following curve ensures that the metal obtained by carbon reduction is in vapor state? So हमें वो फिगर इनमें से आइडेंटिफाई करनी है जिनमें कार्बन रिडक्शन से इंश्योर होगा कि जो कंपाउंड बनेगा, जो मेटल बनेगा, जो मेटल हमें ऑब्टेन होगा वो वेपर स्टेट में होगा. ओके, तो हम ए फिगर को एनालाइज करते हैं. कार्बन मोनोऑक्साइड मेटल को तब रिड्यूस कर पाएगा जब कार्बन से कार्बन मोनोऑक्साइड बनने वाला कर्व वो मेटल से मेटल ऑक्साइड बनने वाले डेल्टा जी उसकी डेल्टा जी कम हो जाएगी, यानी वो कर्व उसके नीचे चला जाएगा. तो इसमें हम देखते हैं कि जो फर्स्ट फिगर में हम देख पा रहे हैं कि जो सी से सी ओ का ट्रांजिशन है और एम से एम ओ का ट्रांजिशन है, ये अगर ये सॉलिड स्टेट रिप्रेजेंट करता है, ये अगर सॉलिड स्टेट रिप्रेजेंट कर रहा है, जो फर्स्ट हाफ ऑफ कर्व है जिसमें स्लोप सेम है, सेकंड हाफ ऑफ कर्व जिसमें स्लोप इंक्रीज हुआ है, वो लिक्विड स्टेट रिप्रेजेंट करेगा. तो इसमें आप साफ साफ देख सकते हैं कि जब सी टू सी ओ कम हो रही है तो वही लिक्विड स्टेट में प्रोड्यूस हो रहा है मेटल. हमें क्या चाहिए, इस प्रोड्यूस्ड इन वेपर स्टेट. तो ए आंसर नहीं होगा. तो अगर हम सेकेंड फिगर देखते हैं तो हम सेकेंड फिगर में देख पाएंगे कि जो सी टू सी ओ है, जो कर्व वो एम टू एम ओ कर्व बनने से नीचे तब जा रहा है जब वो थर्ड हाफ ऑफ फिगर में, यानी थर्ड पार्ट ऑफ फिगर में है. तो इसमें क्या आ जाएगा, इसमें जो मेटल प्रोड्यूस होगा वो वेपर स्टेट में मेटल प्रोड्यूस होगा. तो ये आंसर बनता है. बाकी फिगर्स भी चेक करते हैं. ओके, इसमें हम देखते हैं कि ये तो फर्स्ट पार्ट ऑफ फिगर है, उसी में जो सी टू सी ओ है वो नीचे हो जाता है. नीचे यानी उसके डेल्टा जी की वैल्यू ज़्यादा नेगेटिव हो जाती है. तो उसकी अगर डेल्टा जी की वैल्यू ज़्यादा नेगेटिव हो जाती है तो ये जो मेटल प्रोड्यूस होगा ये सॉलिड स्टेट में प्रोड्यूस हो जाएगा. और डी डायग्राम में हम देखते हैं अगेन ये लिक्विड स्टेट में ही इंटरसेक्शन है, क्योंकि ये सेकेंड पार्ट ऑफ कर्व है. इसमें हमने ये पढ़ा है कि अगर किसी ये कार्बन आइड्स इज अ रिड्यूसिंग एजेंट, कार्बन टू कार्बन मोनोऑक्साइड, दिस प्रोसेस हैज अ डिक्रीजिंग डेल्टा जी विद इंक्रीजिंग टेम्परेचर. सो कभी ना कभी उनकी डेल्टा जी लेस नेगेटिव हो जाएगा मेटल टू मेटल ऑक्साइड से. सो द चेंज विल बी अकम्पनीड बाय डिक्रीज इन Gibbs energy and hence the process would be spontaneous. So the answer for this question is B. We have all the valid arguments for that. Okay, now let us see what is question number 2. Question number 2 says which of the following is not an ore of copper. So हम पहली ऑप्शन देखते हैं एटिकोमाइट. एटिकोमाइट क्या होता है? एटिकोमाइट होता है, हम देखेंगे एटिकोमाइट इज इक्वल टू Atacamite is equal to Cu2Cl OH whole thrice. अब शैल्कोपाइराइट पे आता है, ये भी बहुत कॉमन है, ये तो CuFeS2 होता है. और शैल्कोसाइट पे आते हैं तो वो Cu2S होता है. और सेल्यूसाइट क्या होता है? सेल्यूसाइट होता है PbCO3. सो हमें पता है दिस इज नॉट एन ओर ऑफ कॉपर, सो द आंसर वुड बी दिस पार्ट. Okay, the third question goes like, in which of the following metals extraction process there is no reduction or respective ore or metal in the smelting step. मैं ये बार बार रिपीट करता आ रहा हूँ, लेकिन फिर भी इसका आंसर ऑब्वियस है. हमें पता है इसका आंसर Cu होता है. सो इसका आंसर Cu हम क्यों होता है, क्योंकि हमारा जो ओर होता है जैसे हम ये एक्सट्रैक्ट करते हैं वो होता है Cu2S Fe2S3. तो जब इसके अंदर से हम एक्सट्रैक्ट करते हैं तो Fe जो होता है वो प्रेफरेबली ऑक्सीडाइज हो जाता है, वो FeO बना देता है, जो फर्दर SiO2 के साथ रिएक्ट करके FeSiO3 बना देता है. तो हमारा जो Cu2S है वो रिड्यूस कहाँ पे होता है? रिड्यूस जो होता है वो जाके होता है बेसेमर कन्वर्टर में. तो देयर इज नो रिडक्शन, बेसेमराइजेशन कहते हैं इसे. तो स्मेल्टिंग में कोई रिडक्शन नहीं होता है यहाँ पे. सो द आंसर इज क्वाइट क्लियरली कॉपर.
So now we move on to question number 4. Now the question reads as, among the following, number of compounds that would require electrolysis process to get the respective metal is NaCl, Cr2O3, MgCl2, Al2O3, CaCl2 and Fe2O3.
Okay,
these are our metals, these are our compounds, and we need to find the number of total compounds that would require electrolysis process. So the solution goes as,
So electrolysis process to get the metals. So इसमें refining की बात नहीं हो रही है because we get the metal in reduction process, not in refining process. Refining में हम metal जो मिलता है उसको और purify करते हैं. So हमें सोचना चाहिए उस terms में. तो अगर हम further इसको analyze right, तो NaCl हमें पता है NaCl में हमें इलेक्ट्रो रिडक्शन चाहिए होता है क्योंकि इट इज़ हाईली रिएक्टिव. ना कार्बन रिडक्शन ना थर्माइट रिडक्शन, इस पे दोनों में से कोई भी काम नहीं करता है.
Okay, so students need to remember those compounds which are highly reactive must be reduced by electrolysis.
Cr2O3 हमें याद है थर्माइट से होता है. ठीक है, तो दिस इज नॉट एन आंसर.
Okay.
ठीक है, MgCl2 अगेन बिलोंग्स टू द रिएक्टिव कैटेगरी, सो हम 2 पे पहुंच गए. Al2O3 अगेन बिलोंग्स टू द रिएक्टिव कैटेगरी, सो 3. CaCl2 कैल्शियम अगेन बिलोंग्स टू द रिएक्टिव कैटेगरी, 4. नाउ Fe2O3 पे हम आते हैं. हम मेनली इसे कार्बन रिडक्शन के थ्रू करते हैं या फिर इसमें थर्माइट भी यूज कर सकते हैं जो हाईली एक्सपेंसिव होता है. तो दैट सम्स अप द क्वेश्चन. द आंसर इज गोइंग टू बी 4.
No, so basically only those reactions which are only those compounds which are highly reactive can only be separated by be refined or by electrolysis process.
Actually, it is the opposite of what you're saying. It is the only highly reactive compounds can only be reduced by electrolysis. It is not that electrolysis can happen only for these. Electrolysis can happen for the rest as well.
Okay, so actually the feasibility is only for these highly reactive compounds. Okay. So now we move on to question number 5 of metallurgy. The question reads as, the oxidation state of copper in chalcopyrite is. Here we would definitely need to remember the chemical formula of chalcopyrite. So that's a completely based on memory question.
Okay, memory plus, yeah, you can say memory, but we need to go into a little insight of it as well. If you look at chalcopyrite, many of you would remember it as CuFeS2. Right, but remembering this won't help because it could lead to a confusion whether this is +2 because this is -4 if you see, and or whether it is +1 +3. Both the compositions are possible. Actually, it is this case. The compound exists in the form of Cu2S and Fe2S3. So this is the way, and you can see clearly copper is +1. You need to just remember this. I cannot say much about it in terms of concept.
So there's one question, like if the S2 is it definitely going to be -4 or can it be -2, because we know that S2 - species exist. So
yeah, S2 minus exists, but sulfur's most common oxidation state is -2 sulfide when it exists as sulfide.
Okay.
As the two metals present, so sulfur is likely to be present in the form of its in the least oxidation state. S2 is in the presence of less electropositive metals also.
Okay. So here, as copper and iron are more electropositive, hence S exists in -2 oxidation state. So
Right.
we are done with the question. Now we move on to the next question. Okay, so in the given question, we are given a flow chart that reads as only hematite ore on gravity separation gives concentrated ore, which on roasting gives roasted ore, which on smelting gives slag and molten metal. Now the molten metal on puddling gives wrought iron. Now the question reads as, which of the following steps is unnecessary in the extraction of Fe as shown in the above flow diagram? Options read as A. Gravity separation, B. Roasting, C. Smelting, and D. Puddling. So the answer solution goes as,
सी हमने अभी देखा था बिकॉज इन रोस्टिंग जो फाइनल प्रोडक्ट हमें मिलता है दैट इज Fe2O3, बट हमने लेटर डायग्राम में एनालाइज किया कि इवन इफ यू हैव FeO the reaction proceeds, the smelting can take place without any problem. So you can say the unnecessary step or not so necessary step is roasting. So that is the solution. Roasting is the answer.
so students need to remember like they need to carefully analyze the diagram and hence decide that.
Yeah, exactly. This was discussed during theory.
Okay, so now we move on to next question. So now we'll start with question number 7 of this chapter, metallurgy. The question reads as, which of the following reaction takes place in Bessemer converter for the extraction of copper? It's multi-correct answer, so we need to carefully analyze all the options. Option A is twice CuFeS2 plus 4O2 gives Cu2S plus twice FeO. Option B is Cu2S plus 3 by 2 O2 giving Cu2O. Option C is Cu2S plus Cu2O giving 6Cu plus SO2. And option D is FeO plus SiO2 giving FeSiO3. Now let's start with the solution.
Okay, first thing is most of the reactions are not balanced. So basically what we're going to highlight, what the questioner is going to is trying to highlight in this is the process. So you need to analyze the process, not going to balancing, do not panic if you see that the equation is not balanced. So what is wrong with it? The first thing you need to analyze is copper extraction has 3 processes associated with: roasting, smelting and Bessemerization. So roasting, smelting and Bessemerization process, there are different steps associated with it, and different parts have different functions. So in the first part, we remember what happens in roasting is CuFeS2 gets converted mainly into Cu2S and FeO. So that is the main purpose of it. It is the only process of roasting in which in the initial process where limited amount of oxygen is used, we only get Cu2S and FeS. So and SO2 is also produced. So as a result of which, in this reaction only sulfides are produced rather than oxides. Even in case of roasting, when we heat it with excess oxygen, then iron oxide is produced because it is more electropositive than copper. Then comes your smelting. Smelting converts the rest of FeS into FeO, which combines with SiO2 to form FeSiO3 slag. So this is what happens in smelting. What happens in Bessemer converter is Cu2S, which is converted to Cu2O. Part of it is converted to Cu2O, and self-reduction takes place. That is what is happening in Bessemer converter. Blast of air is passed through it, and initially what we do is remaining Fe. If there is any FeO, it is also added to SiO2 and slag is formed. So what we need to look is which of the following reactions takes place in Bessemer converter. So we can quite clearly see that the first reaction does not take place in Bessemer converter, as I explained. Cu2S plus FeO is formed in the first step, which is roasting. So this is we can easily say that this is incorrect, right? This is incorrect. Cu2S plus 3 by 2, obviously this process takes place in this, right? Now this the third part talks about self-reduction, and that also happens in Bessemer converter. You'll remember what we get eventually is a mixture of Cu2S and Cu2O, and we left it to be heated. We heat it, so as a result of it, what you get is 6Cu plus SO2. Right, and I talked about Bessemer converter as well, that if there is some amount of FeO still remaining after smelting, so that also is removed during Bessemer converter. So this reaction also takes place. So multi-correct answer. It's a multi-correct answer. You need to be really cautious. Some people can get confused with this D part because it's mainly happening in smelting as well as Bessemerization. So you need to take into account that this also happens in Bessemerization. So the answer is B, C, D.
Okay, so now we move on to the next question. So now we would start question number 8 of metallurgy chapter. The question reads as: froth flotation process can be applied for ores other than sulfides using a suitable reagent called which of the following? So actually the question reads as even non-sulfides can also be used for froth flotation process. The options are A, collector, B, activator, C, frother, and D, depressants. The solution goes as follows.
So we've already learned that Na2S can be used as an activator for ores like anglesite. Activator, I've used a term called activator. So you'll see that these can be used. So the answer is, right, I've write Na2S and this is PbSO4. So this is used for this. The answer is activator. So now we move on to the next question.
So this is a factual question, okay?
Yes, it is a factual question.
So now we will start question number 9 of metallurgy chapter. The question reads as: the overall floating of the ore occurs due to option A, absorption process between O particle and collector. Option B, only adsorption between O particle and collector. Option C, adsorption and lyophobic aptitude of collector. Option D, only lyophobic aptitude of collector. Please note that absorption and adsorption are two different things which you must take into account. The solution begins as follows.
Okay, so now we look, we've already told you the structure for a collector, which goes like this. Sodium ethyl xanthate, I just told you about it. So it goes like CH3, CH2, O, C, double bonded S. This is S, I'm sorry, this is S negative Na. So this part prefers to stay in water and this part prefers to stay in air, because this is hydrophobic in nature and this is hydrophilic in nature. One thing must be remembered, that it is the addition of the collector which leads to the development of the lyophobic aptitude of the collector. That is, the sulfur ores are wetted by oil, it is due to the addition of the collector. Okay, so as a result of it, the sulfide particles cling onto this, or we can say adsorb onto the sodium ethyl xanthate, the collector, as a result forming a bubble like structure which results in the formation of froth. So basically two phenomena involved. One is adsorption. So basically one must remember it is adsorption and lyophobic aptitude. You do not need to go into the depth of the question and how this phenomena exactly works. One needs to understand is what is important as answering the question.
So now we begin question number 10 of chapter metallurgy. The question reads as, which is the chief reducing agent if carbon reduction of iron oxides is carried out below 710 degrees Celsius? The options are A. Carbon monoxide, B. Carbon, C. Either carbon or carbon monoxide, and D. Cannot be predicted. So basically the question relates temperature to feasibility. So it can easily be solved by a Ellingham diagram. So we now highlight this in more detail in the following solution.
Okay, so the Ellingham diagram looks something like this. Okay, this is the Ellingham diagram for C plus O2 to CO2, right, as we remember, and there was the Ellingham diagram which went for C to CO, right, but you'll observe that there is an Ellingham diagram for CO to CO2 which increases, CO plus half O2 obviously, right. I'll write it down much more cleanly, right. So there is CO plus half CO2 which is going to happen over here, CO plus half CO2, right. So this is the point of intersection lies at 710 degrees Celsius. So see the graph which lies the graph which lies below most, which lies under everyone, okay, which is below.
So basically the graph, the line which lies which is most below, that is more feasible, you are trying to say.
Yeah, that's what. So in this case, CO plus half O2 to CO2, this line lies below both of them. So as a result, CO is a preferable reducing agent. In case we would have considered above 710 degrees Celsius, then also the process which had been most favorable would have been C to CO. As you can see, the Ellingham diagram.
Because that line is below everyone else. Okay. So this basically relates to feasibility. That is, if delta G is more negative, then the reaction is most feasible. Hence, we are saying that the line which is below others would be more feasible. So this clearly describes, this is a clear application of Ellingham diagram, and we now move on to the next question.